All right, so we're gonna leave stats aside for a little bit, and we're gonna go into the other aspect of the class where you typically, normally it's like stats and probability. We're gonna talk about probability for a little bit, and then we'll go back to stats after midterm. Your next test is actually, as crazy as it sounds, in 2.5 weeks. So, and then your spring break's right after that point. So we have 2 weeks, chapter 4 this week, chapter 5 next week, and then the test week. So I tried to make it so that you didn't have to worry about stuff over spring break. It was a nice, easy break right between them. And then easy for the midterm grades too, which go around the same time. All right, what do you know about probability? When you think of probability, what do you think of?
Likely might get caught, depending on how fast I drive over the speed limit. Get to school on time.
Okay, you can do 80 on Route 2 and not get caught. Like I literally set my cruise control at 80, and I've driven by cops and they've never even moved.
I do 4 miles.
Yeah, I have my cruise control set at 80 on Route 2. So there you go. I don't know about 395. I haven't been on 395 in a while, so but it's 80 on Route 2. So when you're looking at probability, typically the first couple of things that come to mind is flipping a coin, rolling dice, playing cards, things like that. Those are typically when you see probability. Now, when you're talking about probability, there's a very specific way you have to think about it, which is actually kind of what you did. It's the number of ways the event can occur divided by the total number of events or possible outcomes. So that's how you calculate probability. All right. So it'll always be a fraction or a decimal when you're looking at probability, and it will always be between 0 and 1. So 0% probability means the event will never occur. 100% probability means the event always occurs. All right, so that would be between 0 and 1, because your decimal changes to a percent from 0 to 100. Okay. Wrong screen. Can't change that one. All right. So the first thing that we have to do when we're looking for probability is we still have to figure out all the different possible outcomes that we can have. Okay. So, and we'll give you the exact name of that later. We'll talk about it a little bit more later. It's called sample space. So, because when we're looking at the formula, it's the number of ways that the event can occur over the total possible outcomes. So I need to know the total possible outcomes before I can actually do probability. So here's the top 5 top officials in Oklahoma, and they want to take a random sample without replacement of 2 officials. So the first thing we have to do is we have to come up with a list of our possible combinations. Whenever you're doing these, you want to do them in an order that makes sense so you'll get them all. Okay. So for example, I'm going to start off with governor. So I do governor and lieutenant governor, governor and secretary, governor and attorney general, governor and treasurer. So those are all the possible outcomes with governor. Since it says without replacement, I'm not going to have governor. If it didn't say that, I could have governor. Okay? So that's what that without replacement means. That person's not being put back into place. Now we'll move on to lieutenant governor. So I have lieutenant governor. Lieutenant governor and governor, is that the same as governor and lieutenant governor? Yeah, it's the same 2 people. So in this case, I don't need that one because it's the exact same thing. So lieutenant governor and secretary, lieutenant governor, attorney general, lieutenant governor and treasurer. And then secretary and attorney general, secretary and treasurer, and then attorney general and treasurer. So since we don't say, since these are actual like titles, order doesn't really matter. So governor, lieutenant governor, governor would be the same thing. We don't have to worry about that. If we were taking people and then placing them in positions, say we wanted to had 10 random people and we were picking 2 people and we were assigning stuff to them based on where we chose them, then order would matter, and then those 2 would be different things. All right, so how many people do I have? How many different options or combinations do I have? 10. So my bottom probability number will be 10. So how many outcomes did the treasurer get picked in? 4. So the probability that the treasurer would be chosen is 0.4 or 40%. So 4 out of 10, 0.4 or 40%. Those all mean the exact same thing. Okay. So when we're talking about probability, all of them are accurate or accurate. Same rules apply when you're rounding. You want to go to 3 decimal places. So in this case, it's 1, so we don't have to worry about it. How many outcomes does the secretary get chosen? 4. So the secretary is 4 times. Actually, if you looked at this, they will all come out to be 4 out of 10. Because of the way that they were broken down and chosen. Okay. Now, if they all came out to be 4 out of 10, I have 1, 2, 3, I have 5. That doesn't add up to 1, right? That's okay. We'll talk about why that is the case a little bit later. Your probabilities do not always have to add to 1 if certain conditions apply. Okay, because we're choosing 2 different people in each option. So basically, every person can be chosen 4 times. What's 4 times 5?
20.
20 or, yeah, 20 or would be 2, right? If we did it as a percentage. So if everybody could be chosen twice, that makes sense. Okay, because there's overlap. They're not mutually exclusive, which is what we're going to talk about in a little bit. All right, dice. So if you're going to do any problems with dice rolls, I would highly suggest printing up one of these little charts with all the dice. It makes it really easy to be able to choose your dice. Okay. So what's different between this one and the one we just did? All the options are listed there, but what's a couple differences?
Well, then you look at, you can have less probability or probability.
Okay, you're thinking way too complicated.
Okay.
Just looking at the sample space. So just looking at the group, the stuff that's on the screen right now. Forget the probability for a second. What's the difference between this chart and this chart? Yeah.
They have some of the same things. So there's 1, 2.
Okay. So order kind of matters in this situation, or does it matter? Yeah, we have to have it though. We have to have it actually for a more important reason, because what's the big difference between this one and the other one is I have 1, 1. Yeah, I can have the doubles. So I don't have I have replacement here. So I'm rolling 2 separate die. They don't interact with each other. So I have to list all the combinations of those. If you're going to have doubles, you have to list both options of the 1, 2 and the 2, 1. All right. So how many total outcomes are on the screen?
36.
36. So all of my probability will be done out of 36. What is the probability that the sum of the dice is 11? So we're going through and adding them up. Honestly, what's the highest sum I could get? 12. What's the lowest sum I can get? 2. Okay, so they're probably going to be down towards the bottom thing. So it's like if you look at it, it's actually just those 2. So it's 2 out of 36. Is 0.055 or 5.5%. That you're going to get a sum of 11. What's the probability that doubles are rolled? So I have 1, 2, 3, 4, 6. So it's 6 out of 36. So it's 167 or 16.7%.
Couldn't you simplify those 2 fractions and you would still get the same answer?
Yes, you could simplify the 2 fractions. You do not have to, though. In this situation, just changing it to a decimal is going to give you most of the information anyway. So I would rather you divide it and get me the decimal than worry about simplifying the fraction possibly incorrectly. So,
When do we have to simplify fractions in this chapter? If you know.
you really don't. Because everything, so probability can be listed as any of those options. So because we're going to be doing other calculations and stuff with it, and since you can give me it as a decimal, I would just give it to me as a decimal in this situation. I wouldn't necessarily have to reduce the fraction. If you do, I'm not marking it wrong. It's totally correct.
Since,
Just you don't have to.
since probabilities are related to relative frequencies.
Yeah.
It
Yeah, it's always as percentages, which is fine. What wonderful casino game is this going to help you at? It's craps. The one game in casino that I have yet to figure out how to play. Apparently, it's actually the best game to play. Like, in terms of probability, you have the best chance of winning playing craps. But I've yet to figure out exactly how to play it.
You know how to play poker?
Yes. Actually, poker is the one game where probability does not help you very much at a casino. Because in every other game that you play at a casino, you're playing against the house. You're not playing against everybody else sitting at the table. In poker, you're playing against everybody sitting at the table. You're not playing against the house, which changes how you do the calculations. Like even in blackjack, you're playing against the dealer. Everybody sitting at the table, doesn't matter what they get. You're literally just playing against that one person in front of you. So that's how poker is actually done quite differently in terms of a casino. What are these 2 things? So these are tossing a coin. Yeah. So if I was to give you a coin and have you toss it, could you get 5 heads in a row? Yeah. And it's not that unlikely to get 5 heads in a row. It's like it can happen. If I was to ask everybody in this classroom to flip the coin, could everybody in here get 5 heads in a row? Could it happen? Yes. Would we all go out and play the lottery? Yes. But the more and more you do it, the more unlikely that it occurs. Okay. So we have a difference between what's known as experimental probability and theoretical probability. Theoretical probability is what we were just getting. All right. 6 out of 36 is the number of evens or number of doubles that you can get on dice. That's a theoretical probability. If you were going to play the game, odds are you're probably not going to get exactly that. That's what the coin flipping is. When you flip a coin, that's an experimental probability. How many times did you get it out of how many times you flipped it? The more and more you do it, the closer and closer it should get to a theoretical probability. What's the theoretical probability of flipping heads? 50-50, right? 1/2, 50%. And if you notice, these two tosses, as they start getting more and more, they start getting closer and closer to that 50%. Okay? And doing 100 tosses isn't a lot. So you get closer to like 1,000 or 10,000, it's like you're going to get pretty close to that exact 50-50. But you're not getting exactly that. You might have, out of 1,000, you might have 510 heads and 490 tails. Like, but if you look at that, that's 51%, which is pretty close to 51.49. That's pretty close. So that's when you have to start looking at the difference between when you're playing a game and what should happen. It's like if you go to play roulette, roulette's completely probability based. So the odds of, here's an interesting question. Let's say, what are the odds of hitting black or red on a roulette wheel? It is 18 and 18 because there's 36, but there's not 36 numbers. Right, there's 38 numbers. So the odds of hitting black is not 50%. The odds of hitting red is not 50%. It's 18 out of 38. That's the house. The green numbers are the house where the house makes their money. It's not that you can't bet them. It's just that's what shifts the odds from exactly 50-50. If it was exactly 50-50, if there was no green on the wheel, the casino would make $0. It would make no money. Because over time, it would split exactly even. You would win as much as you lost. But because the greens are in there and their odds are still based on it being 50-50, that's where the casino makes their money. Because your odds aren't exactly 50-50. So the more you play, eventually you're going to lose a little. Not a ton, but you're going to lose some. So, all right, we talked a little bit about this. This is just written down stuff that I've already basically mentioned. Probability event is always between 0 and 1. Inclusively, you can have 0%, you can have 1%, or you can have 0 probability, you can have 1 probability. So it'd be 0 to 100 if you're looking at it in terms of percents. If the probability of it is 0, it never occurs. Okay. So that'd be, let's say, like, what's the probability that pigs fly? It's not going to happen unless they're shot out of a cannon. So, like, that's something that will never occur. What's the probability that you'll walk? You're going to walk. It's like that's 100% probability. So those are the differences there. When you're playing games of chance, those two pretty much never occur. We talked a little bit about this. The sample space is key. That's going to give you all the possible outcomes that you're going to have. So we did that at the beginning with the governor, lieutenant governor, secretary, attorney general, treasurer. We made up the sample space. Whenever you're looking at probability, we need to know what it's coming out of. Okay, because that's going to give you your bottom number. If we don't have that bottom number, we can't figure out your probability. So when we're talking about a roulette wheel, your sample space is 0, 00, and then 1 through 36. If you're talking about craps, that's the 36 dice rolls that you just saw. Okay. If you're talking about blackjack and poker, it gets a little more complicated. The event is the collection of outcomes for the experiment. That's what we're looking at. And that can change. So when we're looking at dice, you can have a ton of different events. You don't have to necessarily have just one event. The sample space probably won't change, but the events do. Any questions on those? Some of the stuff you probably have not heard before. Some of the stuff you might have heard. As a math teacher, I always like teaching probability because we would literally sit there and play games, and kids like playing games. So for a while, until people started to get edgy about it, we used to actually have my seniors used to create casino games. They'd make their own game systems up, and we'd play the games in class. So. All right, let's look at a deck of playing cards. So a deck of playing cards contains 52 cards. As crazy as this is, I learned last class I taught this. This is not something everybody knows. 52 cards. There's 4 suits: clubs, hearts, spades, and diamonds. The cards are from ace to king. What are your face cards?
Jack.
How many face cards are there?
16.
There's 12. The aces are not face cards.
But can it be like 1 and 11? So
No, so the ace could be 1 or 11, depending on what you're playing, absolutely. But a face card has a face on it. So, and as crazy as it sounds, like I told you, I'm writing a book, and we put problems in the book that dealt with cards. And people were coming up with different answers for when we asked for face cards. And that was the problem. So we actually literally go online and do a ton of research to try to figure out, is it a face card is just Jack, Queen, or King? And that was then being the consensus behind it, because they have faces on it. The ace doesn't. People sometimes look at the ace as a face card because it's the highest card, but it also could be the lowest card, depending on the game's played. So an ace is really 1. But those are things that you have to think about when you're looking at things. So now when we write it, I write face cards: Jack, Queen, King, in parentheses next to it. So this way it's like everybody's on the same page. All right. We have 13 cards in each set. 2 sets, or 2 of the faces are black and 2 of the faces are red. So 2 of the suits are red and 2 of the suits are black. So that's my sample space for this. All right. So what is the probability of getting a black card? So the probability of getting a black card is not 50-50. I understand what you're saying, and you're correct, but that's not the probability. The probability is 50%. Okay? So it's important, because that's the only one that you'd ever say that to. Like if I asked you what's the probability of getting a club, you're not going to say 25-75. All right? You're going to say 25% or 1/4. All right? So we're talking about reducing fractions. The probability of getting a club would be 13 out of 52. We typically wouldn't say that. We would say 1/4. So both those are going to come out to be the exact same percent. And that's why getting into a decimal will take care of 99% of those issues. Because you divide it, you're going to get 0.25 no matter which one you actually start up. Okay. What's the probability of getting a face card? 12 out of 52. Because there's 12, and my sample space has 52 cards. Okay. Yeah. When we're talking about these, we don't add the 2 jokers in, which is also some of the things that people wanted to do. I'm like, no, jokers are not part of the deck.
what are jokers?
They're wild cards. It just depends on the games you're playing. All right. Let's see. So when we were looking at the cards and stuff like that, I basically only asked you for one thing. I said, what's the odds of clubs, or what's the odds of a face card, or what's the odds of a black card? It was one thing. However, you can ask more than one thing. So when we're looking at asking for events, sometimes combinations of events are more than what we're looking for. So it'd be, what is the odds of a black face card coming out? Now we're looking at two different events, correct? We're looking at a black card and a face card. Okay. Or what is the odds of a even red card? Okay. So those are two different events. What's the odds of a black 5 or a red 7? Two different events. Notice how I asked the difference in those two things, those things though. So the black 5, that's one card, that's an and. It has to be both those, right? If it's a black 5 or a red 7, now that can be either or of them. So that's an or. So that's the difference between and or. And both those things have to be true for it to work. Where an or means either one of those can be true. So it could be a black 5 and you win, or a red 7 and you win. But it can't be a black 4. Because that wouldn't work. So that's the ands and the ors. We also can have not the event, like I don't want an even card. Or you don't want to roll a 7 in craps if you just rolled a 7. I'm almost positive that's don't want to roll back-to-back 7s. It could be the opposite, though. It could be that you actually want to. I honestly, that's the one blame I said. I cannot get all the rules down. So we have our wonderful little horrible drawing. What's this called? Anybody remember the name of this?
Venn diagram.
This is a Venn diagram. So a Venn diagram is just a graphical representation of sets. They have no actual like necessary meaning behind where the circles are and stuff like that. But there's a couple things on this one that are important. So all the orange in the very middle, right there, that's A and B. That's the overlap between them. Okay. If it's or, it'd be anything in A or anything in B, which means that piece in the middle also occurs. And that's fine. So or includes where they both happen. And then the not would be everything else except for what was inside the circles. So that's just a nice little graphical representation of the ands and ors. Remember when we were talking about when I said that there's differences when they're mutually exclude, like when they don't overlap. Okay. That actually has a lot of meaning and usefulness. When two events are mutually exclusive, there's no overlap between them. All right. So are clubs and spades mutually exclusive?
Yes.
Yes. There's no overlap between a club and a spade. Okay. Those would be two completely distinct probabilities. Are even cards and red cards mutually exclusive? No, because there's our even cards that are red cards. Okay, so that's the key. It's you don't want an overlap. If they're mutually exclusive, there is no overlap between them. Okay, if all the events are mutually exclusive, my probabilities will add to 1. All right. So if I said all the black cards and all the red cards, so the black cards are 1 out of 2 or 26 out of 52. The red cards are 26 out of 52. If you add those together, you get 1. Those are mutually exclusive. If I look at all the even cards and all the red cards, however, there are even cards that are red cards, so they will overlap. So that if I added those two percentages together, that's not going to necessarily work well for me to get to the 1. So when we're talking about the governor, lieutenant governor, that first example, when I said the probability didn't add up to 1, it's because they weren't mutually exclusive. Okay. The secretary, when I counted all the secretaries, that was 1%, that was 4 out of 10. When I counted all the governors, it was also 4 out of 10, but there was a governor and secretary in there where they overlapped. So they were not mutually exclusive events. Okay. Does that make sense? No? All right. Let's look at some examples. All right. So here's my 4 events. The event A is the card selected is the King of Hearts. Event B is the card selected as a king. So let's define the probabilities of each of these real quick. What's the probability that I'm going to select the King of Hearts? Just 1 out of 52, right? There is only 1 King of Heart in the entire deck. Okay. What's the probability that the selected card is a king? 4 out of 52. There's 4 kings. What's the probability that the selected card is a heart? 13 out of 52. Or 1/4 if you want to look at it that way. What's the event that card is a face card? We've done this one already. 12 out of 52. Okay. All right, so those probabilities are really easy, right? To get. Okay. What's the probability that it is not D? So if we wanted to do not D, that is the opposite of what I had, right? I don't want those 12 cards. So not D is 40 out of 52. All right. What's the probability that B and C occur? So that means they both have to occur. So B says it's a king,
1 out of 52.
and C says it's a heart. This is the difference.
16.
Okay. It says B and C. So B and C is different than B or C. Hold on one second. So B and C means they both have to occur. You actually have the answer first. What were you going to say? So the answer is 1 out of 52. There is only 1 card that is a king and a heart. Okay? So that's 1 out of 52. What's the probability that it's B or C? So-
No, and a king, so it'd be the other, so it'd be 16 out.
Is it 16 or 17?
16.
So why is it 17? Okay. It's 17. Good. Why is it 16?
Because the king is already a heart, so it'd be just 13. Well, it's actually, so it'd be Orsi, and then, because there's already 3 kings, and one of the kings is already a heart, so it'd be 13 plus the other 3 kings, so it'd be 16 out of 52.
Okay, who's right?
Come on, dude. I'm gonna say me.
That's the difference between when things are mutually exclusive and when they're not mutually exclusive. These two events are not mutually exclusive. If they were, you'd been right. It'd been 17. You can add the 4 and the 13. Okay. However, as you mentioned, there's one card that overlaps. Okay. There is a king that is a heart. Okay. So they are not mutually exclusive. So I cannot just add the 2 of them together to get the total percentage, the total probability. I have to remove that extra count that I did because that king and heart is counted in both of them. All right. So if you look at it the way you did, you said I have 13 hearts, and then I have 3 other kings that were not already counted. And that's where the 16 out of 52 came from. Does that help understand mutual exclusive a little bit better? Okay. So that's really the key piece in there. All right. What was the other one? C and D.
So the answer is 16 out of 50.
The answer is 16 out of 52.
Oh, sorry.
That's good.
Still on thinking.
No, you're fine. But yeah, that's the difference between mutually exclusive and not mutually exclusive. All right. If I had asked, actually, none of these would fall into not mutually exclusive, or none of these would end up being mutually exclusive the way you wrote the events, which is fine. This one works out better, or these actually give me some other options.
So that's sort of visual. Would have assisted the rest.
Absolutely, because you can look right at the cards. Yeah, like you could literally just pick the cards and go, "Oh, okay, that's where I'm counting them," and that's also where understanding what card, like the actual cards, are important in that situation too, because not everybody knows what a deck of cards looks like. Which, like I said, that was a shock to me when I did this class last time. I'm like, everybody's played with a deck of playing cards. No, they have not. All right. So now we're going to look at if the events are mutually exclusive or not. Okay, because like I said, that's probably out of everything when we're looking at probability, one of the more important things. Because when we're looking at cards, you can physically look at the cards and figure it out. It's pretty easy. But when we're starting to get to larger probabilities and things that we might not be able to visualize as easily, understanding if it's mutually exclusive or not tells me which formulas I need to do. Okay. And when we're starting to put things together, those formulas are going to start to help me out a lot more. So understanding what mutual exclusive is a very important piece to this. All right. So we've got the selected card is a heart. The event is a face card. The event is a ace. Remember, an ace is not a face card. The event card is selected as an 8, and then the event card is selected as a 10 or a jack. All right, so C and D. Is C and D mutually exclusive or not? No. Because there's face cards that are hearts. Okay, so those are not mutually exclusive. C and E. Is there a card that fits both C and E? Yes, then they are not mutually exclusive. Okay. So this is no, they're not mutually exclusive. Actually, I probably should write the question in here.
So if there's no overlap
Yes, yes. That's what you're looking at. Is there overlap or not? D and E. So face card and an ace. Is there any overlap? So that is yes, that is mutually exclusive. So those two are mutually exclusive because there is no overlap between those. D, E, and F.
Yes.
Oh, wait.
So the question is, are they mutually exclusive? Yes, they are mutually exclusive. There is no overlap. Okay, because there's no overlap between face card and ace, and eight's not a face card or an ace. So there is no overlap between those. So those are mutually exclusive. All right. Good. I didn't ask about G at all. G and D. We'll do that one just because I didn't use the G one at all. Why? Because the Jack's a face card. All right. So D was face card, and E was ace. So what's the probability that I would get a face card or an ace? So a face card is what? 13 out of 52, right? And an ace is, oh no, sorry, not 13, 12 out of 52. And then that's 4 out of 52, right?
Yeah.
So that means I would get the 16 out of 52. Okay, because there's no overlap in those at all. All right, so if they're mutually exclusive, I can just add the two things together. C and D. C was a heart, right? Which is what? 13. And D was a face card, which is 12 out of 52, right? So if I added those, I would get 25 out of 52. But there's overlap in these, right? So if we go back to my cards, so it was hearts. And it was face cards. So those right there. So if we counted them up, we'd have 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I'd have 22, not 25. Okay? Because those cards right there are counted twice. Okay? So when they're not mutually exclusive, I have to subtract off the cards that are counted twice. So I get 22 over 52. You have
The
to,
cards that are counted twice.
in this case, it's the heart of Jack, Queen, and King.
Heart of Jack, Queen, and King.
Yeah. Because we counted them as hearts, and we counted them as face cards. So since they're counted twice, I have to subtract off that extra piece. Okay? That's why it's important to know, are they mutually exclusive or not? Because if they're mutually exclusive, I'd be subtracting nothing because there's no overlap. So I don't have to worry about that part. If they're not mutually exclusive and there's overlap, I have to subtract that part off when I'm looking for my probability of combined events. Okay? All right, so here's the formula that we just did. If the events are mutually exclusive, then you can just add the probabilities together. Okay. If they're mutually exclusive, you can just add the probabilities together. And that counts for as many events as you want. All right. So if we're looking at a coin, are heads and tails mutually exclusive events? Yes, you can never get heads and tails at the same time. So that's how you get 1/2 plus 1/2 is 1. Okay. So that's if they're mutually exclusive. You're also, oh, actually, while I'm on the screen, because there's actually something you're going to see quite a bit. This is the notation you're going to see. That P, this stands for probability. Inside here, it can be a letter, or it can be what the event is. So if it's going to be a letter, somewhere you have to tell me what that letter associates with the event. So like in the last examples that we did, I gave you, I said A, B, C, D, or C, D, E, F, G. Those were all events that I gave you there. So I could have said, what's the probability of C? What's P of C? All right. So if you remember back to your algebra class, remember f of x? Kind of the same thing. It's the function of x. This is the probability of A. All right. It just makes it, it's just a shorthand to write whatever my events and stuff are. If they are not mutually exclusive, we have P of A plus P of B minus P A and B. So that's the overlap. Okay. Now, technically, this rule works for everything. Because if there's no overlap, what's that going to be? 0. So you just subtract 0. So it doesn't really make a difference. That's why this is called the general rule, because this works for technically every example, even if they don't overlap. But you're subtracting off one of those because you're counting it with A and counting it with B. So you want to subtract off 1 because you only want it once, not twice. All right. Are we good up to that point? Anybody totally lost at this point?
I think the equations make a lot more sense.
It's like sometimes it's one of those like half dozen or it's like I could show you the equations first and say here's the equations, and then I could show you the problems and people go huh, because they'll look at the equations like it'd be confusing. So it's like, or I do the other direction. It's like they both, you need them both. So it's like you need each reasoning. Sometimes I like showing an example first, especially with cards and dice and stuff like that, because most people have done those things or played with those things before. So it's kind of like, it's like, oh, okay, that kind of makes sense. Like you can, and then you see the equations like, oh, okay. I guess it really depends on if you're a visual person or an equation type person at that point. So, but getting them both definitely does make things click a lot better. All right. So let's look at this. So so far, all the problems that we've done, we've looked at very like games, cards, dice, things like that, that were simple cases. However, probability can be used in anything. Okay. And one of the things that we're eventually going to get into is what is the probability to select a certain person out of a bell curve? Like when we're looking at like z-scores and stuff like that, that's the probability that that event occurs. So these things go beyond just games. We've got, this is the size in acres of property. All right, so we've got the size in acres under 10, 10 to 49, 50 to 179. So is this, if I was to graph this, is this a proper histogram? What? Right. Okay. My classes are not equal. Okay. Under 10 is 10. 10 to 49 is 40 of them. 50 to 179 is now 130. So they're not equal spaced. All right. Are these events mutually exclusive? Is there any overlap between these events? No, you can't have 180 acres and 40 acres. Okay. So these are mutually exclusive events. So if I was to ask you, what is the probability that the person has under 180 acres? How would you find me that answer?
Under
Under 180.
yeah, everything under 180.
Right. So if I said under 180, I'd be adding up those three probabilities, correct? All right. If I said between 50 and 500, between 50 and 500, you'd add those two. Between doesn't mean equal to 500. This is where sometimes how things are worded matters. If you were doing, if you wanted the, actually, technically, I would have had to say between 49 and 500, because you wouldn't want the 50, but you would say inclusive if you want to include those values. Okay. So if you just see the words between, it typically just means between, doesn't mean equal to those values at the end. If it says inclusive of the endpoints, then you'd actually add those in. And then, yes, I would have a little bit of a trouble with the way this is set up because I'd have to find 500. What if I said greater than or equal to 10? I want everything more than 10 acres or more.
Out of the first one, or that thing,
What would be the easiest way to do this?
100 minus 1.06,
Well, I would do 100 minus 1.06.
or
I would do what minus 1.06?
1.
1. If it was percent, I would do 100. So if it was 10.6%, I could do 100 minus the 10.6%. Since these are in relative frequency as in decimals, I would do 1 minus it. So one of the ways that we can do this sometimes easier than sitting there adding them all up is if I want everything except for one thing, in essence, I want not that. That is 1 minus that percent that I have. So when I said everything greater than 10 acres or higher, I would do 1 minus the under 10 acres. Okay. Or when they said less than 2,000 acres, I could do 1 minus whatever the 2,000 acres was. So, and it would save me the trouble of going through and adding up a bunch of extra numbers. There it is. Let's do that one. Let's do this one. All right. Last problem of the day. So data on people who've been arrested. So arrest characteristics are published every year by the FBI, broken down into region, by state, everything else. So you can easily get all this data. This is data that's actually used quite a bit to look for patterns, to look for inconsistencies. So if you have a police department that has a very high percentage of males being arrested that is unusual as compared to the national average, there might be concerns there that you can look at. Or if they're more like blacks and minorities are being arrested, that we use that data to show discrepancies in information. So records for 1 year show that 73.9% of the people arrested were male, 12% were under 18, and 8.5% were males under 18. If a person arrested that year is selected at random, what is the probability that that person is either male or under 18? So, question 1. Are these two events mutually exclusive? No. Because you could be male and under 18. So, we can't just add the percentages together, correct? So, we need to subtract off the overlap. Luckily, they gave me the overlap. So, what's the percent that is male?
73.9.
That's male. What's the percent that's under 18? 12%. And then we want to subtract off male and under 18, which is what? 8.5%. All right, so what is the probability that the person is either male or under 18? 76.4%. I didn't do it, so I'm going with what you did. That sounds about right.
77.4.
77. That's okay. There you go, 77.4%. Because they were not mutually exclusive.
Why would we subtract the 8.5% but not the 12%?
Because 12, so the two events that I'm looking at are male. So that's the probability of male
Probability of male being
is 73.9, right? The probability of under 18 is 12%, right? And then it's minus the probability of male and under 18, which is the 8.5%. Okay.
Was there any overlap? No.
Yes, that was at 8.5%.
Yes.
That was the overlap. Because these are not mutually exclusive. You could be male and under 18. And 8.5% of them were male and under 18. So you want to subtract that off because they've been counted in the males and in the under 18. So we would subtract off that 8.5%.
Not mutually exclusive then.
Correct.
That's what you're trying to say.
What's the percent of...
What is
Thank you. What's the percent of females in under 18? What is the percentage of females that are under 18? What was it? How'd you get it?
You just subtract the male under 18.
Very good. So we know that 12% is all the under 18.
Yeah.
And we know that 8.5% of those are male. So that would mean 3.5% are female and under 18. What's the percent of females? Total.
26.1.
26.1. We would just subtract the 73.9 from 100. Okay. So actually with this one, like with the data they gave me, you could actually figure out quite a bit of information. The setup of it all. Okay. So this, I wanted to end on an example that didn't directly relate to a game. So this is where those conversations and those things happen. Okay. Yes.
Right now in the border, they just did this. We statistically found almost all men were being arrested for illegal crossing, not women and children.
Yep.
So it looks like they're gonna start arresting more women.
Right. And so it's like, then you got the question is like, okay, is that the direction we wanted to go?
I'm just saying.
No, I know, but that's
I know.
right. But and those are the things that you look at. It's like,
Someone looked at that and said, "You're arresting more women or not all?" I don't know.
yeah, it's like, and so, and that's where you start to look at the probabilities and the percentages and stuff. It's like, this is how this data is really being used.
Or the cartels look at it, and now they're using women as the donkey.
Yeah.
To bring drugs. Right, is that really the issue?
If you didn't get your test, come up and get your test. Because I know some people came in late. I didn't hand them up to you before you came in. First thing. Right on top. You're welcome. First thing.
Logan. Thank you. We're allowed to take these?
Yes.
Thank you.
You're welcome.
Or-
What's